All right, thanks for tuning in. This is a brief presentation on atomic weights, how to calculate them. But before we begin, I just want to give a quick shout out to that amazing Period 6 chemistry class. And also, this podcast is brought to you by Cornell Notes. When you want to take notes well, it's Cornell. Okay, so here we go. As we've been looking at the periodic table, and as you've been looking at over the years yourself, I'm sure that there have been moments when you've noticed these numbers inside each rectangle, each element, that are these decimal numbers. And you may have a sense of what they mean, but they are probably a little bit more mysterious than the whole numbers, right? We know the whole numbers are atomic numbers, and it's very clear what those are related to. But numbers like 1.008 for hydrogen, where in the world does that come from? This is what we call the atomic weight of the element. And as we're going to see, just in brief, I'll just tell you that they're an average value of the atomic masses of the isotopes, all of the isotopes that exist for hydrogen. Okay, so we'll get a feel for that. That's job number one here in the next 15 minutes. Okay, so let's consider a system like a collection of marbles that is a little bit more intuitive, something we all have experience with. And then I'm going to try to gradually make the analogy to atoms. All right, so let's say you've got this collection of marbles at home, and they're all in a basket, and you pull 10 marbles out, and you sort of sort them by the mass, and you notice that you've got 9 marbles that are at 10 grams, and then you have one marble that is 20 grams. Okay, so you could, if you were really bored, you could plot or create a distribution plot for the masses of those marbles. So you'd have a scale, a mass scale right here, and you would just put one dot for every marble that has this mass. So you'd have nine circles above the 10 gram value, and you'd have one circle above the 20 gram value. And so that's sort of a histogram of the distribution of marble masses. Now, what if somebody asked you this question? If they said, hey, what's the average mass of your marble collection? Well, you could do that, right? I mean, that's just, pretty simple math. You've got 9 marbles at 10 grams apiece, so altogether these have a mass of 90 grams, and then there's the one that's 20 grams, so that'd be 120. I'm sorry, 110. I guess I'm bad at math. So if you set it up in a formula, you'd have 20 grams plus 9 times 10 grams, which is 90, and 90 plus 20 is 110. And then to get the average, you would divide that total by the number of marbles altogether, which is 10, and you'd come up with 11.00 grams, right? Okay, so that's pretty straightforward. Now, the problem is that when we go over to the world of atoms, it's very hard to count individual atoms. I mean, they're super small. There are just jillions of them, an unbelievably large number of them, and so you simply cannot count the atoms, the individual atoms of a given element. It's just too much. And so I want to take we're going to divert for just a minute here and answer the question, so how actually do you measure atomic mass and eventually come up with an average atomic mass? Well, as you can see here, you do it with a very sophisticated machine called a mass spectrometer. And here's a picture of a mass spectrometer in a laboratory. And what they do, it's pretty wild. If you have a sample of, let's say you had a sample of chlorine atoms, like we were talking about today, you would inject that sample into the mass spectrometer. It goes down this tube, and they're clobbered with a beam of electrons, high energy electrons. And what that does is it knocks some electrons off of the atoms and they become charged. Okay, they have like positive charges because they lose some electrons, and then they feel the effects of this electric field. They get accelerated through that little hole in that disk, and then when they get here, as if losing electrons isn't bad enough, then they get subjected to a strong magnetic field. And as you may remember from physical science or middle school, when a charged particle is moving in a magnetic field, it wants to move in a curve. Okay, so it feels a force, it changes direction, and then they make their way down here, and this is where they hit the collecting screen, and depending on how far the charged particle was deflected by the magnetic field, it'll have a different position. It'll strike the screen at a different position, and the lateral position, the relative position of those different ions is related very, very precisely to their mass. And so this eventually gets turned into a spectrum. Okay, this is called a mass spectrum, and it's a bit simplified, but it's very realistic. This just happens to be the mass spectrum for atomic chlorine. And what you get is you get two peaks. One is at a mass of 35 and the other is at a mass of 37. And the height of these peaks is in a very particular ratio. The peak at 35 mass units is 3 times, very close to 3 times taller than the peak at 37. So it's about a 3-to-1 ratio. And it turns out that the taller peak corresponds to chlorine 35, okay, and that's where the 35 comes in, and the isotope chlorine 37 is responsible for the peak at 37, as you would have guessed. Now, let's get back to the marbles. Okay, so back to this situation. You could imagine a scenario where you don't know the exact marble count, right? But if this was done in, say, a mass spectrometer, you would know the percentage. You'd know the relative height of these two peaks on the mass scale. And so, if you had 9 and 1 marbles, that would translate into 90% and 10%. There's a 9-to-1 ratio between those two. And I'm going to show you a way, of calculating the average when you don't know the count, but you do know the relative percentages. And it's really neat, and it's very straightforward. So all you do is for each type, each different mass of marble, you simply multiply the mass by the decimal value that corresponds to the percentage. So 10%, when you convert that to decimal form, is 0.10, 90% is 0.90, and so you can see, 10.1 of 20 is going to be 2 grams, and 0.9 of 10 grams is 9 grams. 9 grams plus 2 grams equals 11 grams, and we get the exact same value as we did calculating the average the old-fashioned way, a few slides ago. Okay, so this I want you to remember. This is the way that we calculate average mass in the context of atomic mass. Okay, so back to the chlorine spectrum. As you can see, there was this 3-to-1 ratio, and a 3-to-1 ratio is the same as 75-25. 75% chlorine 35, 25% chlorine 37. And so now watch the magic. So here I'm setting up the same type of average calculation as we did before with the marbles, except now instead of grams we have a unit called AMU, atomic mass unit, and that's what you guys were reading about today. So the peak at 35, that's the 75% we convert that to 0.75, and then over here we multiply the 37 atomic mass unit peak by 0.25. And when you do that, you get 35.5 AMU. Okay. Now, take a look at this. This will blow your mind. If we go back to the periodic table, let's find chlorine. All right, there we go. The actual atomic weight is 35.45. Pretty close. The reason we didn't get 35.45 on the button is I'm using somewhat it's basically 75-25, but it's a little bit just slightly different from that. And when you use more precise values from mass spectroscopy, you will get the 35.45 that's on the periodic table. One more thing here. In terms of terminology, the proper term, the more specific term is average atomic mass. But in the literature and in many textbooks, rather than spelling this out, they just call it atomic weight. Okay, and so it's kind of for historical reasons. So going forward, when we talk about atomic weight, we specifically mean the average atomic mass of all the isotopes of a particular element. Okay, all right, let's move ahead. Here's one more example. Let's say we've got this situation. We've got an element with two isotopes. They both have 6 protons, so you can guess what element that is, right? The first isotope has 6 neutrons, therefore the mass number is 12, so that's carbon 12. The other isotope has 7 neutrons, and so that's carbon 13. If you put carbon into a mass spectrometer, what you will see on the atomic mass unit scale is 98.89% of the carbon atoms have a mass of 12, and 1.11% have a mass of 13. And so now we have all the information we need to calculate the average atomic mass, right? So let's do that. So here's the data in table form, and what I'd like you to do is push pause and see if you can use the example from the last slide and calculate the average atomic mass. Okay, so what is the average atomic mass or the atomic weight? Hopefully you set up your calculation like this. So you have the mass, 12 AMU, times the fraction of the sample that has that mass, which is, when you convert this percentage to a decimal form, it's 0.9889, plus 13.003 AMU times its corresponding decimal value. Okay, so I hope I'm not confusing anybody by going between the percentage and the decimal form. Okay, that's if you get thrown by that, just take the percentage, take your calculator, divide that by 100, and then you'll get the decimal form. You always have to use the decimal form of the percentage when you're doing these average calculations. And when you do that, you should get 12.011. I hope you did. And then maybe you snuck a peek at the periodic table, and did you notice that the atomic weight for carbon is in fact 12.011? So amazing. There's no mystery at all. Okay, so this is the very last slide. What I'd like you to do is pause the video now and fill in all of the information in this table for these 3 isotopes of oxygen, and then I'd like you to use this information to calculate the atomic weight of oxygen. Okay, so how'd we do? Hopefully you got 8 protons for each, and then in the neutron column you got 8, 9, and then 10. Here is the atomic weight calculation. So starting with oxygen 16, you simply take convert the percentage into a decimal, multiply that by the atomic mass. You do that for all 3 isotopes, Notice it doesn't matter which order you multiply these in. The AMU can come first or second. And when you crank all that through, you should get 15.999. That's to three decimal places. And if you check the periodic table, I think you'll find that we're very close. Okay, so thank you very much for listening, and I hope that was helpful. See you tomorrow.